stay tomorrow to stay today until really early tomorrow. So if you talk to him today if you need. So quickly to summarize his Bruce's life. Bruce started to work with Spitzer at Cornell where he got his PhD. And then moved on to a first postdoc at CITA, a second postdoc at the Institute for Advanced Study in Princeton, and since then he has been a professor at Princeton University. And today he's going to talk about the properties of dust in the SIMS sample.
Thank you very much, Brice. So, thank you very much for inviting me here. And today I'm going to try to tell you a little bit about dust. A few people in this audience know more about dust than I will, but Peter will have to be polite. It's specifically going to address the dust as studied by the SINGS Galaxy survey in the infrared and the deductions that we can make from that. So let me first give you some credits here. So the modeling which is going to be described here is going to be based on modeling of the dust extinction curve by Joe Weingartner, who was a CITA postdoc some years back. The infrared emission models that are going to be described here work with the same dust that Joe modeled. That was work done with Eigen Lee when he was a postdoc at Princeton. He's now at the University of Missouri. And then they're going to be applied to observations taken with Spitzer Space Telescope as part of the Spitzer Infrared Nearby Galaxy Survey, which was one of the legacy projects that Rob Kennicott was the PI on. Okay, so we're going to be talking about the infrared. So let me remind you what we know about the infrared. Actually, we're talking about interstellar dust. Let's start with that. So when did we first know that there was such a thing as interstellar dust? I think the discovery paper on interstellar dust actually goes to William Herschel. And here is the text of that paper, published in 1785. And what was he doing? He was actually working with a very modern technique. Try this again. He was working with a survey instrument. There it is. So at least a facsimile of it as rendered by the artist. So this was a telescope. He set it up, and he just sat and watched the stars roll by and did star counts. He was trying to understand the structure of the universe as observed from the Earth, and he perceived that a good way to study this was to analyze the mathematical distribution of stars. And so he was just sitting there, we didn't have automated recorders. He would just watch the stars going by and describe how many stars he could see. And I guess he'd have an assistant, a sister maybe, who would write these things down. And then one night, as he says, and I'll read you the text here, he says, I found it while I was gauging in the parallel from 112 to 114 degrees of north polar distance. As I approached the Milky Way, the gauges, the star counts, the visual star counts, have been gradually running up, and then all of a sudden they fell down to nothing. And so he's describing here that some parts of our system, an opening in the heavens, some parts of our system, namely the universe, the galaxy, indeed seem already to have sustained greater ravages of time than others, if this way of expressing myself may be allowed. For instance, in the body of the scorpion, because he was doing this particular observation in Scorpio, is an opening or hole which is probably owing to this cause. So he discovered interstellar obscuration, but of course had no idea, did not have a correct understanding of what it was. But this is the kind of phenomenon he was seeing. Regions where there were lots of stars and regions nearby with very few stars. We now understand this is a result of the extincting of light by the dust in clouds of stars. And we can study this as a function of wavelength. So here it doesn't come out too well, but as you move from the visual wavelengths where this particular cloud, B68, is completely opaque, to the infrared, you do it K-band, you can begin seeing background stars here. So the attenuation of light is wavelength dependent, and that wavelength dependence is something we can now measure quantitatively. We can also study dust by the fact that it scatters and reflects light. So this is a familiar reflection nebulosity, the Pleiades. So we can quantify our studies of this reflecting properties of the dust grains, and whatever we end up thinking interstellar dust is had better be consistent with these scattering properties. We can also study interstellar dust not by the wavelength-dependent extinction, but by the polarization-dependent extinction. So when we observe a distant star through the dust in the Milky Way, the light reaching us is observed to generally be linearly polarized. And here's a map of the polarization vectors of the electric field vector in galactic coordinates for about 3,000 stars located within 1 kiloparsec of us. Here's the galactic plane, here's the galactic center, and you can see that there's large-scale coherence here. Nearby stars have similar directions and similar magnitudes of linear polarization of the light reaching us. And we understand that is coming from the fact that the dust grains are not round, not spherical. They have to be non-spherical and somehow systematically aligned in space, so they're better at extincting or attenuating one polarization mode than the other. Okay, so those are different ways we can study dust grains at optical wavelengths, but we have another powerful way to study dust, and that's by using the infrared, also discovered by William Herschel. So here's Herschel actually doing the artist's conception of the discovery experiment, where he took sunlight, refracted it through a prism, and put thermometer bulbs down in different parts of the spectrum, and he noticed that when he moved his thermometer even beyond the red, it would still warm up. So he noted that there was some sort of energy or heat delivered by invisible light, and we now understand this is just the infrared part of the spectrum, which our eyes are not sensitive to, but which carry, in the case of the sun, considerable energy. So now we can study the universe at infrared wavelengths. And here's an image of the sky, not at optical wavelengths, but at about 100 microns, taken by spacecraft, in particular IRAS, and then supplemented by COBE. And this doesn't come out too well here, but it's a beautiful image of the galaxy, again in galactic coordinates, showing that there's a great amount of the infrared luminosity. The surface brightness is concentrated in the galactic plane, peaking towards the galactic center. A great deal of structure here, if one could see the lower brightness levels. But we are not seeing starlight here. Virtually none of these photons came from the surface of a star. Essentially all of them, almost all of them, came from emitted by dust grains. So we're observing the galaxy by the glow of dust grains. So this is the galaxy by dust glow. Okay, so why do we need to understand dust? So some of us are fascinated by it, but other people may regard this as just really a messy and not very interesting problem. But in fact, it's an important problem. So first of all, astronomers want to understand why things look like they do. And in fact, dust shapes the appearance of many objects by its differential extinction, both in position on the object and as a function of wavelength. So if we want to understand the appearances of things, we'd like to understand what the dust is doing to be able to estimate what the intrinsic luminosity spectrum of an object would be. In addition, the dust emits at long wavelengths. So if we talk about what things look like, well, if we want to look at what galaxies look like in the infrared, in the far infrared, we are looking at emission from dust. So the dust properties are going to be an important part of understanding that story. Now, galaxies are powered by stars, so when we look at galaxies, most of the energy flow through the galaxy is originating in nuclear processes in stars and then transmitted by starlight from one point to another. That energy, of course, requires the formation of stars, and at least in the contemporary universe, the star formation process seems to involve dust grains as a very important part of the dynamics of collapsing molecular clouds. So that, if we want to understand star formation today, you want to understand what the dust grains are doing dynamically in that gas. And in fact, if you want to understand the interstellar medium in general today, you find that dust grains are playing an important part in many different activities in the interstellar medium. They can regulate the ionization in some regions by providing places where ions can find electrons. They can regulate the properties of the radiation field by attenuating it and allowing some regions to be shielded from starlight and therefore allowing molecules to be present there. In fact, they act as sites for molecule production. So the whole chemistry of the interstellar medium basically starts with molecular hydrogen formation of dust grains, and then things happen after that. And they, in fact, play an important role in heating much of the interstellar medium. So if you want to understand the thermal state of the interstellar gas, much of it is dominated, the thermodynamics is dominated by photoelectric heating, photoelectrons coming from dust grains. And even in the fluid dynamics, the radiation pressure forces exerted on dust and then transferred to the gas can be a very important part of moving gas around or sustaining, opposing the forces of gravity in various circumstances, both in the Milky Way and in more energetic systems. So understanding the dust is important. So this is just a list here just to remind you that our study of dust actually brings together many different lines of evidence. So as our understanding of dust grains today, incomplete and tentative as it is nevertheless constrained from many different sides. So I've already talked about some of these. That we observe, we measure the wavelength-dependent attenuation of starlight. We make a dust model today, it had better be consistent with that. The dust grains must be able to scatter starlight in approximately the way we observe. They must be able to polarize starlight, at least if we can invent a way to explain the alignment of the dust grains. We can also observe the scattering of light not just at optical wavelengths, but even at X-ray energies. So when we look at an X-ray point source through the interstellar medium, there's in general a halo of small angle scattering of X-rays around it. And our dust model had better be able to quantitatively reproduce that property of that effect of the dust grains. The infrared and submillimeter emission, I showed you that. In fact, that's going to be what I'm going to concentrate on in this talk. That emission, in fact, ought to be polarized, so it's difficult to measure today, except in particularly bright places. But WMAP, in fact, is already making statements about the polarization of the submillimeter emission or the microwave emission from the 90 gigahertz submillimeter emission from dust grains, and Planck is going to be showing us even more about that. So it behooves us to try to understand that as best we can. And in fact, the dust grains not only radiate thermally, but some of them they're all spinning, and some of them are spinning rapidly enough that their electric dipole moments as they spin generate measurable amounts of microwave emission. So in fact, that's an important foreground that CMB experiments have to deal with. And again, our dust model had better be consistent with that observed property. Now, indirectly, we can study dust grains by seeing that certain elements are missing from the gas phase. So we can measure the abundances of the elements in the gas phase spectroscopically by doing absorption line studies towards bright ultraviolet, towards hot stars. And then we observe that we can measure the abundance of hydrogen and oxygen and so on in the gas, but we observe that certain elements like iron and silicon seem to be extremely underabundant in the gas relative to what we expect based on solar abundances or other estimates of the overall abundance of the interstellar medium. And the only explanation for that is that those elements are missing because they're in dust grains, and our dust model had better be consistent with holding enough of those elements to keep them out of the gas. That's actually not the hard part. The hard part is that you want to make your dust model and not use elements that you're not allowed to use. So the observed gas phase abundances, in fact, constrain dust models. Now, indirectly, you'd like your dust model, if you ultimately understood things, to have the chemical properties and the photoelectric heating properties consistent with other observations of the gas. Now, in some cases, we can actually study interstellar dust grains, or grains that were once interstellar, directly. So meteorites, when they formed in the early solar system, trapped in them some grains that were definitely pre-solar. We know they're definitely pre-solar because they had unusual isotopic abundances and could not have been synthesized in the solar nebula. Therefore, they had to be solid before the solar nebula formed, and therefore they were interstellar grains before the interstellar nebula formed. At least they were part of the interstellar grain population. So we can actually study those directly, and those studies inform us to some extent about what's likely to be out there in the interstellar medium today. Unfortunately, the grains that we were able to identify in meteorites are probably non-representative interstellar grains. They're exotic ones. And so it's been the amount of information we get about today's interstellar dust population is from this approach is so far limited, but the continuing cleverness of the people who study the grains in meteorites and discovering new ways to identify pre-solar grains may eventually lead us to the point where we can perhaps get a more representative estimation of that. And finally, you can actually study interstellar grains entering the solar system today. Right now, they're entering the solar system because the interstellar medium is flowing by the solar system, or the solar system moving through the interstellar medium, depending on how you want to look at it. And the grains that are in the interstellar medium many of them are just simply flow through the solar system. And if we put spacecraft in their way, they impact those spacecraft, and the collisions can be recorded, and things can be learned just about the statistics of those collision events, and ultimately we may be able to capture the elemental abundances of those, capture the grains to the point of being able to study the elemental abundances. Okay, so that's just a long laundry list, but I want to emphasize that all these different avenues are fruitful ways to attack the problem of trying to figure out what interstellar dust is. So let me just remind you what the extinction curve is. So this continues to be a very important constraint on dust models. So I've plotted here inverse wavelength. Zero inverse wavelength is infinite wavelength. So that's the radio region would be out here. Moving towards 1 over lambda equals 10 inverse microns. That's 1,000 angstroms, 0.1 micron wavelength. That's the vacuum ultraviolet with the Lyman edge being somewhere about here. So you basically can't study the extinction properties of dust grains over at higher energies or shorter wavelengths until you get all the way out to X-ray energies and the dust grains become important again. But this part of the spectrum of the extinction law can be studied by looking at stars, comparing them to the observed spectrum of the star with what you think its spectrum would be if there were no intervening extinction, and therefore deducing the wavelength dependence of the extinction. And when we do that, there are some conspicuous spectroscopic features, namely a big bump at 2175 angstroms. The carrier of this bump continues to be controversial despite the fact that it's a really strong feature. We're not sure what it is, but almost certainly it's carbonaceous, and probably it's carbon in aromatic form. So I think that most workers in the field would agree on that, but exactly which form of carbon continues to be debated. Now, there are no other strong spectroscopic features until you go out in the infrared. So now I've blown up this part of the range from 0 to 0.5 inverse microns and expanded the scale. And then you can see that there are two conspicuous features at 10 and 18 microns, which we do understand. We're confident that we identify those as amorphous silicates. Exactly what composition amorphous silicate remains controversial, but it's definitely amorphous silicate. There's no other plausible explanation for the strength of those features, and the features are where you find them if you make amorphous silicates in the laboratory. Now, there are actually some other little features here which look like dirt on this plot. There are hundreds of them. They're called the diffuse interstellar bands, and it's like one of the great embarrassments of astrophysics is that we've had these diffuse interstellar bands known to us for 80 years now, and not one of them has been identified. So there's someday we're going to hit the jackpot and begin understanding what these are. They're probably small, due to very small dust grains, perhaps polycyclic aromatic hydrocarbons, but we don't know for sure. And then there's another weak feature at 3.4 microns, which is a carbon-hydrogen stretching mode, probably in chain-like hydrocarbons. So I've dwelt on this a little bit too long, but again, this is an important constraint on interstellar dust. So now let's move into the infrared. So infrared observations have been carried out with a series of space missions going back to IRAS. COBE had infrared capabilities that were very important. The ISO satellite was fantastic in breaking new ground, both in photometry and spectroscopy, imaging and spectroscopy. But more recently, Spitzer Space Telescope came on the scene. Not a terribly big telescope, 85 centimeter aperture, but has the virtue of having liquid helium-cooled optics and enough cryogen to last for 5 years plus in space and solar orbit. It was launched in August 2003. It's still working, and the helium is probably going to run out about April of next year. And until then, it's been a fantastic instrument, and it may continue to do some observations after that at the shorter wavelengths, but it's going to lose its long wavelength capability. So it can image at 7 bands from 3.6 to 160 microns, and it has a low-resolution spectrograph or moderate-resolution spectrograph that works from 5 to 38 microns. Now, we'll show you examples of both photometry, the imaging with the different cameras, and the spectral results. So the SINGS project was approved as a legacy project, and the objective was to look at 75 nearby galaxies, near enough to us that we could resolve all of them with the resolution of Spitzer, so you could form images of all 75 galaxies, even at the longest wavelengths, and diverse enough that we'd be covering a broad type. So there's no way with a count of 75 galaxies you could cover every corner of galaxy parameter space, but it is a broad sampling of galaxy types, including dwarf galaxies and genuine, healthy star-forming galaxies. It doesn't include any extreme AGNs or anything, but aside from that, it's a representative sample of galaxies. And here's what the very first one in the survey looked like. This one happened to be the one that was imaged first. We think it looks a lot like what the Milky Way would look like from outside in its general distribution of stars and gas. So this is an image taken with the IRAC camera, and if you break down the wavelength range from the two shortest wavelength bands of IRAC, you're basically looking at where the stars are. So most of the photons in this image are starlight photons. But if you go to the two longer wavelength bands of the IRAC camera, most of the photons detected by this camera are photons that were radiated by polycyclic aromatic hydrocarbons. So we're seeing this galaxy is easy to detect in the PAH emission features. They're all over the place. They're strong. They're carrying a significant fraction of the energy, as you'll see from the spectra. So now here are also some spectra of some of these galaxies, including NGC 7331, which we just looked at. But it's not the spectrum of the whole galaxy. It's a spectrum of a central region where we were able to take spectra using all of the observing modules of the infrared spectrograph. And so the regions are large, but they don't contain the whole galaxy, and roughly these are the linear dimensions, you know, a few kiloparsecs depending upon the distance of the galaxy from us. And you see in every one of these spectra that are shown in this sample of 6 from a larger sample, these pH emission features in the 5 to 17 micron range are very strong. You see them in galaxy after galaxy, and these are absolute spectra. This is the true zero level. The spectrum is typically rising as you go to longer wavelengths, and much of the power is out here at long wavelengths. But there's a lot of energy in this part of the spectrum, and I've plotted this as nu I sub nu. So it's power per logarithmic interval in frequency, and this is log frequency this way. There's a fair amount of area under these features, and you see they're detected with very high signal to noise in these particular spectra. Well, we'll talk about where this power is originating, because that's a somewhat controversial point, but I think we can say something about it. Okay, so how do we proceed with the dust modeling? Well, it'd be nice if we could just say, oh, well, let's start with Schrodinger's equation, but that's ridiculous. The problem is just far too hard. So we have to start with assuming a physical model. So we're just going to make some assumptions, say, I'm going to assume that dust has such and such physical properties. But once I've made that assumption and specified it, then I'm going to say, okay, if I put that dust grain out there, what will be the wavelength-dependent extinction of those physical dust grains? If I illuminate them with starlight, how will they be heated by that starlight? How will they radiate in the infrared? And I'll be able to calculate properties of the dust model, but I'll need to make some assumptions about what that model is. And of course, the game is to then calculate everything you can that's observable, compare with observations. If it agrees with observations, you're delighted. If it doesn't, then maybe you can figure out what needs to be changed in the model and come up with something that's closer to the truth. And as the model matches more and more things, you'll never think it's an exact description of the dust grains, but you'll be confident that you're capturing more and more of their physical attributes and can make reliable inferences about things like dust masses and starlight intensities in these galaxies. And that's going to be our aim here, to make these inferences about what's going on in the galaxies in our sample. So the model is described, has been through some evolution over time, but the latest version of the model is not really very different from what it was 6 or 7 years ago. So it's a model that I've been developing with Eigen Lee, where we simply start with the same dust model that we were working with previously with Joe Weingartner, in fact going all the way back into the 80s, a model where about half the dust mass is silicate, or half the dust volume is silicate and half of it is carbonaceous. The only difference in the last 15 years is that we recognize that the carbonaceous dust, a substantial fraction of that, has to have the physical properties of polycyclic aromatic hydrocarbons. I'll talk in a moment about what these are. Now, these are the materials that we're assuming, and we don't know everything about these materials because they're not things you can order from a chemical supplier. And he says, oh, you ask for interstellar grain material of these two kinds, they can't deliver it to you because we don't know exactly what it is. And carbonaceous material includes a vast range of possibilities. Amorphous silicate, well, there are different ways of making amorphous silicates. There's no well-defined thing there. But roughly speaking, we know what the physical properties of these are going to be. And so we'll write them down. We'll say, okay, well, this is what we're going to assume as a function of wavelength for the dielectric function of amorphous silicate. Or this is what we're going to assume as a function of wavelength for the absorption properties of polycyclic aromatic hydrocarbon molecules. And then we'll try to find size distributions that actually reproduce the observed extinction. So we'll now constrain the sizes, and that's the work that Joe Weingartner did. And we find that we can do that. With these two materials, by adjusting the size distribution, we can not only reproduce the observed extinction on the average in the Milky Way, we can reproduce the variations in the extinction from one sight line to another by just adjusting the size distribution. And if we go to the large and small Magellanic Clouds, we also find that these two materials, changing only their proportions and their size distributions, can reproduce the extinction curves we observe in these two nearby galaxies. And unfortunately, we don't know much about the extinction in other galaxies, but this three galaxy sample covers a wide range in metallicities. And so if we're matching these three, we have some confidence that maybe we've got a model that is describing cosmic dust, or at least a good part of it. And then with this model, we can just put the grains into a specified radiation field from stars and calculate how they're heated and how they're going to emit. And then if we can calculate an emission spectrum and we compare to observations, we can adjust the assumptions on the amount of starlight heating here to try to get the best match to the observed infrared emission spectrum. So what are these polycyclic aromatic hydrocarbons? Well, it's a class of molecules of this general form. The carbon is arranged in this hexagonal pattern, just as it is in graphite. So a sheet of graphite consists of carbon organized in exactly this way. So you could think of a polycyclic aromatic hydrocarbon as taking a piece of graphite, which is this crystal of pure carbon, breaking off part of one sheet, and then just letting hydrogens attach at the edge. You now have a polycyclic aromatic hydrocarbon. That's probably not how, that may not be how nature makes them, but that would be a way of forming them. You'd get exactly what I'm talking about. And here are just 4 particular examples of the polycyclic aromatic hydrocarbons. And here's a spectrum taken by the ISO satellite of a reflection nebula, NGC 7023. ISO and its predecessors were only able to get high-quality spectra of high surface brightness objects. So we tended, in those days, we tended to know a lot about the spectra of bright things like this particular reflection nebula. We'll see now, we've seen how Spitzer now enables us to get similar quality spectra averaged over the disk of another galaxy. Now, these emission features which are seen in this spectrum can be identified as characteristic vibrational modes of this class of molecules, but you can't, they're all broad, and you can't say specifically which molecule it is, and in fact, we don't think it's one molecule. But nature is making many different molecules of this characteristic form, and there's a mix of these pHs with different sizes out there. But the particular features we see in this spectrum, we think we can identify with particular vibrational modes of either the carbon skeleton, in these 2 features, the carbon skeleton. This is the carbon-hydrogen, with the hydrogen wagging up and down, rather in the plane at the edge of the molecule. This complex of bumps is the hydrogen wagging up and down, transverse to the plane of the molecule. Okay, so coming back to these spectra, again, I just want to emphasize they don't all look identical, but you are struck with their similarity. These very different galaxies seem to have a lot of commonality in the relative strengths of the pH emission features. So it's reasonable to say, hey, let's try one mix of pHs and see if we can reproduce all galaxies, at least all the ones in our sample. Okay, so how do we go about this modeling process? Well, as I said, we have a physical model here. We make assumptions about how many grains of which sizes and composition we have. Now, for each of those grains, we imagine exposing it to a radiation field, and now we recognize that the heating of the grain is a stochastic process. The photons are absorbed one at a time, and they're absorbed at random times. And so the temperature versus time of a grain, even at one as large as having a 100 angstrom radius, over the course of one day, this is 10 to the 5 seconds, would look something like this. Large spikes upward every time a photon is absorbed, followed by gradual decay as infrared photons, many infrared photons are emitted for each optical photon, this optical or UV photon. Then another photon is absorbed, and it's a stochastic process. And the smaller the grain is, the more exaggerated it is, because the photon absorptions are less frequent, but the heat capacity of the grain is smaller, so each time a photon is absorbed, it jumps up to a much higher temperature. And so if you come down to a grain of the size 20 angstroms with, say, 4,000 carbon atoms, it's going to absorb about 1 photon a day. And a smaller grain in the course of this one random day may not have absorbed a photon. Now, for each of these sizes, and of course, as you get to the bigger sizes, the absorptions are frequent enough that you can begin talking about an average temperature. You say, okay, this grain is, let's just say it takes 19 degree temperature, that'll be fine. We don't have to worry about this jitter up and down. But for a grain like this, you have to worry about the jitter up and down. There's no average temperature that would make sense for describing any of the thermal properties of that grain. You have to look at the probability of finding the grain at different temperatures. So you have to solve for the probability distribution function, the probability of finding a grain in some temperature interval t to t plus dt for each composition and each size and each radiation field that you're using. So if you can solve for that, and that's just a statistical physics problem to solve, but if you can solve for that, then you can integrate over the size, over the temperature distribution for one grain to get its time averaged infrared emission, and then you can sum up over all the grains in your model to get the time averaged emission from the whole grain population. So that's the game, and if you raise the temperature of the raise the intensity of the radiation field, of course, all these temperature distribution functions change. The big grains get hotter, the small grains undergo temperature excursions more frequently. And so you've got to solve this temperature distribution function for each radiation field that you have in your model. Okay, well, if you do that, go through the mechanics of those operations, you can now calculate for your grain model what its time averaged emission spectrum would be for each different radiation field that you consider. So these are all radiation fields that are assumed to have the wavelength dependence of the local starlight, diffuse starlight background where we are in the Milky Way. So that includes light from a whole mixture of stars around us, but scaled by a scaling factor where 1 would give you the value we see around us, but 10 to the 4th would be saying the same spectrum but 10,000 times more intense. And you see the infrared emission spectrum of the big grains. They get hotter and hotter, and they radiate at shorter and shorter peak wavelengths as you raise the intensity of the radiation field. But notice the pH emission features, they're nearly invariant. Now, I've normalized this here, so obviously the power goes up as you raise the starlight intensity, but I've divided by this scaling factor, so all these curves have the same area under them. But the shape of these features and their relative strengths is hardly affected, even when you get up to 10,000 times the local starlight background, because again, the grains that are emitting over here, they're just doing this one photon at a time. They simply do it more, or rather they're absorbing one photon at a time and radiating all that energy away and going down to cold state before they absorb the next photon. They simply do it more frequently in the more intense radiation fields, but the emitted spectrum is unchanged. Now, one thing we have to adjust in our models, or can adjust, is the amount of the PAHs that are present in the model. So I'll be speaking about a parameter, Q sub PAH, and let me define that. I'll define that to be the fraction of the total dust mass that is in the form of polycyclic aromatic hydrocarbons containing less than 1,000 carbon atoms each. So that's specifically what I mean by Q sub PAH. And we will vary this up to values as large as 4.7%. We think that that's about the value that would apply to the Milky Way. In some sense, we know these things better for other galaxies than for the Milky Way because we're sitting in the middle of the Milky Way and it's hard to study. Okay, so the SINGS Nearby Galaxy, Spitzer Infrared Nearby Galaxy Survey, I've already told you this, but one thing I didn't tell you is that some of the galaxies in our sample have additional photometry done with scuba at 450 and 850 microns. So in some cases, for 17 of our galaxies, we've supplemented the Spitzer observations by longer wavelength observations, which is very important for giving us confidence in the modeling. Okay, so what are our parameters? If we go model a galaxy spectrum, I'm going to show you some galaxy photometry, and what can we vary? Well, obviously, a priori, we don't know how much dust a galaxy has in it, so that's one of the knobs we can turn. A lot of dust, a little dust. Another thing we can adjust is the fraction of the dust which is in this PAH fraction, because we will see that galaxies do vary in this. So this has to be something which we adjust in our dust model. Now, the other things we can vary will be the properties of a starlight, and a galaxy is going to have a whole range of starlight intensities in it. There isn't going to be one starlight intensity for a galaxy because some dust will be near OB stars and it'll be brightly illuminated, but other dust will be out in the cirrus. So we have to have some way of describing this distribution of starlight intensities. Now that's a hard problem. The right way to do it would be to say, oh, let me just make some assumptions about the distribution of gas and dust and stars in the galaxy and solve the radiative transfer problem, then I'll know. But obviously we can't do that today. We don't know enough about the distribution of the dust and gas and stars and galaxies to even set up that problem. And if we could set it up, we don't have the machinery, the computing power to be able to solve it except in one or two cases with a lot of work. So that's not a practical way to approach it. What we've tried doing here is adopting a simple functional form to parameterize the distribution of what fraction of the dust mass is exposed to different starlight intensities. So we used a power law distribution where we say the fraction of the amount of dust d sub md that's exposed to starlight intensities in the range u to u plus du is just proportional to u to some power, where u is just a scaling factor for the starlight intensity. But we find we also need to let a large fraction of the dust be in a delta function component, where the starlight, where much of the dust is actually, well, let's see, let me jump along here. No, sorry, I thought I had a slide explaining that. So let me just state, we will in fact assume that most of the dust in a galaxy is illuminated by one starlight intensity. Even though I told you right at the beginning, oh, that's not realistic, there's going to be a whole range. But we find that if we assume a single starlight intensity for most of the dust, and then let some of the dust be exposed to more intense starlight, that we do a very good job of reproducing the photometry. A good enough job that there's no justification today for getting more sophisticated about our distribution function. So here's what the photometry looks like for this galaxy, which I showed you before, NGC 7331. So this is the global SED of the galaxy. We've integrated over the entire size of the galaxy out to quite faint regions. So we captured essentially all the power coming from the galaxy. And in fact, we've got even 2 micron points here from 2 mass. So this is 2 mass. This is the 4 IRAC bands in the red triangles. This is Spitzer 12 microns. This is MIPS 24 microns. This is IRAS 12 microns, IRAS 60 microns, MIPS 70 microns, IRAS 100 microns, MIPS 160, SCUBA 450, SCUBA 850. Now, the red triangles here, the horizontal extent is roughly the width of the photometric band. The vertical height is a plus or minus 1 sigma estimate of the observational error. The triangles that have been plotted in each case is the model convolved with the bandpass of that particular instrument. So if the triangle falls inside the rectangle, that's agreement to within 1 sigma. And you see that surprisingly often they do agree. And this galaxy has maybe better agreement, has relatively good agreement, maybe just by luck. I should say the solid line here is the model. So the model consists of a starlight component here, which is basically an almost Rayleigh-Jeans spectrum out here. You don't really need to say exactly what the temperatures of your stars are, but this is a 5,000 degree black body plotted here. So at the shortest bands, we are seeing starlight, but over here we're completely dominated by the dust emission. So it's the sum of the starlight and the dust components is the purple lines. And there actually are 2 models here, just showing that if we change our modeling assumptions, we end up with very similar parameters. So what do we get for the parameters? This galaxy, for the adopted distance, our best estimate of the distance, we have 10 to the 8th solar masses of dust in this required to reproduce this emission spectrum. And the starlight intensity, the average starlight intensity, dust-weighted average, turns out to be 3.2 times what we think the local Milky Way value is. So we didn't end up with exactly the local Milky Way parameters. We get a more intense radiation field for this galaxy. But coming back to the dust mass, we have independent observations of this galaxy in 21 centimeter and in CO. The 21 centimeter we can quite directly get an atomic hydrogen mass from, which is reliable. So 10 to the 10th solar masses of atomic hydrogen. The CO observations, you need to make assumptions about what the molecular hydrogen mass is inferred from a CO luminosity, but with a reasonable conversion factor, we come up with more molecular hydrogen than atomic hydrogen by a factor of 1.6. But if you add these 2 gas masses together and put them into the denominator, we get a dust to hydrogen ratio for this galaxy of about 0.43%. That's dust mass per hydrogen mass. I'm not including helium because the hydrogen is the thing that we observe more directly, but just multiply by 1.4 in the denominator if you want to include helium. Now that's a reasonable number because if you look at the local Milky Way, this galaxy has a metallicity that's like the local Milky Way metallicity. And if you take the local Milky Way metal abundance and look at just those elements that are depleted into dust grains, the answer, you get something like 0.7%. For this number. So we're getting a number here which is surprisingly close to what we would have expected a priori. But we got it blindly because we went out and just modeled the infrared emission and got this number by just letting the computer run over the model. We have a model space here, and we let the computer run over the model space and find the best fit to the photometry. And then we looked up and see what the radio observers say the gas mass is, and lo and behold, we get a reasonable dust to gas ratio. Now that gives me confidence that we're doing something reasonable here, that the model is not too far from reality. But this is only one galaxy.
What's driving the dust mass?
What's
in the spectrum?
Well, just if you scale the dust mass, the whole infrared emission would go up. So the absolute level of the infrared emission here. Well, everywhere where the dust emission is, if you kept the dust properties constant and the starlight heating constant, and just double the dust mass, all of the infrared emission that, from this wavelength longer is going to go up by a factor of 2.
Sure, but most of the mass must be in the bigger grains.
Yeah, well, most of the mass is out here, but the small grains are not a trivial part of the mass, but they're more important in the energetics than in the mass. But the dust model is one, as I said, which reproduces the Milky Way extinction law. We don't know what the extinction law is in NGC 7331, but hey, if we have to assume something, let's assume Milky Way extinction.
So you could get it just from the short wavelength observations. You don't have to have the 100 micron.
You could get it from the short wavelength observations if you thought this was the overall spectrum. But as we're going to see, this part of the spectrum relative to this varies in different galaxies because the PAH fraction does not seem to be constant.
Okay,
So
this is really driven by the pH, the small.
oh, all this over here, these are the pH features. So we're getting the pH mass from these. The pH mass times the starlight intensity is from these. The peak of this spectrum here tells you a lot about what the starlight intensity is because as you make it grains hotter, you'll shift this to shorter wavelengths.
So you're only seeing the grains which can see starlight directly?
Correct. So there could be grains in dark, there must be grains in dark clouds.
Would that be in the Milky Way?
Well, look at this. We have the grains which see the starlight directly, and we've assumed far infrared and submillimeter properties for these grains that are consistent with the COBE observations of the Cirrus. So COBE's, the PHI-RAS instrument, to get into details here, the PHI-RAS instrument looking at the high latitude sky was able to make statements about the spectrum of the infrared emission in the Milky Way in the diffuse dust going from 100 microns all the way out to longward of a millimeter. And we've adopted dust properties that are maybe not exactly the ones you would have gotten from COBE, but are quite close to reproducing the COBE observations. And that was by intent. So we made sure that our dust model, before we started, would be consistent with the Milky Way long wavelength emission, because a priori we don't know that much about the physics of dust grain optical properties at those frequencies. It's still a controversial and confusing subject, what the far infrared properties of dust, of the materials, and particularly materials when they're in the forms of small particles should be. But empirically, we know a lot about that. Now look at this spectrum here. So we reproduced the 160 micron. In fact, we're even a little bit low. The model's slightly low. And we're reproducing 450 and 850 with only this dust. Now, I'm sure that there is colder dust in this galaxy, but the point is it's not emitting very much out here. Maybe it's adding 20% here or something. At the 20% level, we don't know what's going on here. But it's not an important part of the energetics. It might be an important part of the mass. But if it were an important part of the mass, then we might have expected this number to come out really low, assuming that we're getting a reasonable estimate for the hydrogen. And then that's another story. Do we really measure the hydrogen mass, molecular hydrogen mass in dark clouds? But the point is, for getting to dark clouds, we seem to be getting a reasonable story, which tells me that the dark clouds are not dominating either the mass, and they're not even making a significant contribution at the longest wavelength here. And that's not surprising, because the dust, as long as they don't dominate the mass, they're not going to dominate out here, because a warm dust grain emits better at 850 microns than a cold dust grain. So if there were equal amounts of dust grains at 20 degrees and at, let's say 7 degrees, whatever you think a cold cloud is, the 20-degree dust grains are going to win at every wavelength, even the long wavelengths. And so unless you move into some day of precision observations and modeling here, it's going to be very hard to look at the global emission and really make claims that there's really cold dust out there. You could do it perhaps for galactic objects where you can zoom in, but globally it's going to be a hard story. So the story here is that globally we can get along without talking about a significant amount of material in very cold clouds. Sure. It could be wrong. Could be. Okay, so I've been through this, and then time is marching on here. So just here's two more examples of galaxies that, in fact, have SEDs that are quite different. This galaxy, you can see the 70 micron point in nu F nu or lambda F lambda is above the 160 micron point, but only slightly. Here it's way above it. So the dust in this galaxy is much hotter than the dust in this galaxy. In this case, we don't actually know the hydrogen mass because the CO observations have not been done. But in this case, we get a dust to hydrogen mass, even for this very warm case, which is very much like the NGC 7331 number, but with a starlight intensity that instead of being on the average 3 is now 15 for this galaxy. So we're looking at galaxies that are quite different from one another and getting what seem to be reasonable answers in the end. So now let me talk about the statistics of what we're finding here. So dust to gas mass ratio. So I've described how we get both of those numbers. I've plotted them here on the vertical axis for 60 of the galaxies in our sample. Now it turned out we had 75 galaxies in the sample, but not all of them were well detected at the longest wavelengths. And so if we can't detect them at 160 microns, or we're not sure about the detection, we're not going to include them here. So this is the 60 for which the photometry is good in all 7 Spitzer bands. Every point here is the... Okay, so what plotted horizontally here is the metallicity of the galaxy. So expressed in the usual oxygen abundance, where the Milky Way value would be about 8.6, and it's a logarithmic scale, so a factor of 10 below Milky Way would be 7.6. So we have about 1 decade of oxygen abundance, where the oxygen abundances were gotten from studies of H2 regions in the spectroscopy of optical lines of H2 regions. And assume that, and it's all been done in a consistent way by John Moustakis. So the galaxies are plotted on this plot here, and for the moment ignore everything over here. I'll explain this in a moment. But above this line here, you can see that the galaxies cluster around a trend line here, and this trend line is just put in here so that at the Milky Way metallicity of 8.6, it has a dust to hydrogen ratio of 1%. And I said the Milky Way value is probably 0.7%, so close enough. And then there are a factor of 2 variations shown around it here. And within that envelope of plus or minus a factor of 2 around that trend, many of these galaxies are falling inside there. Now, many of them have upper limit symbols, and that's formally there because in many of them the CO has not been reported. And so we don't know. There might be a lot of CO in those galaxies, but in fact the galaxies for which the CO is not reported tend to be the galaxies that don't have much CO in them. And so in fact, most of these cases, the actual value will only be slightly below the point which is plotted here. I'm confident of that. There's not likely to be any of these cases that is really a CO-rich galaxy that was overlooked. The blue symbols here are the ones where, in addition to the Spitzer observations, we have the submillimeter, the scuba observations. So those ought to be the best constrained ones. And you see they also fall within this factor of 2 envelope for the most part. So what this is telling us is that galaxy after galaxy, at least above this metallicity line, have about the same fraction of their metals in dust grains, because the dust mass is proportional to the oxygen mass, right? So this is oxygen abundance. And if we were to have a constant fraction of the oxygen, a dust mass proportional to oxygen mass, we'd have a straight line on this plot. So most galaxies, in other words, are like the Milky Way, where most of the elements that can go into dust grains do go into dust grains. Most of the silicon, most of the iron, most of the magnesium, much of the carbon are in dust grains in the Milky Way, and it must be true in these other galaxies as well. Now what about down here? Down here at first sight, it looks like there's some real outliers here. Holmberg 1, Holmberg 2, DDO 53, they're way below this trend line. But that's actually because what I've plotted here are global values. I integrated up over the entire emission from the galaxy, and I integrated up over all the H1 that's associated with this galaxy. But these galaxies all have extensive H1 envelopes, and only the center of the part of the galaxy is actually emitting infrared. So we really shouldn't be summing up over this H1 envelope. We should restrict our aperture to the region where we actually had infrared emission detected. And if we do that, you get these green points. You look a little bit faded up here, but you correct these up here, and now I say I'll only include the H1 within the region where, projected on the region where the infrared emission is observed. And now, many of these points are now up on this trend line. So at least down to metallicities that are 1/10 of solar, we seem to be seeing the same fraction of the heavy elements being present in dust grains. So that's conclusion number 1.
How extended are these H1 envelopes?
Oh, at this point, I don't want to, I'm sure there are people in the audience who know Holmberg 1, Holmberg 2, and DDO 53 better than I do. I don't remember the numbers, but it's in our paper. So we describe the sizes. Okay, so just to summarize the statistics of the starlight, and I apologize, we're past the 4 o'clock mark here. So this is a distribution of the starlight intensity in this delta function component, which I label U min. So remember I said that most of the dust is exposed to one starlight intensity in each galaxy, and this is what that value is. So 1 would be the local Milky Way. It seems to be more common to be a little bit above that value, but these points, for the most part, are just a few times the Milky Way, the local Milky Way starlight intensity, except for a few outliers here where it's really high. And those are galaxies which, when you look at them, are blue star-forming galaxies. The mean starlight intensity, let's just jump past that. And now let me talk about this. So now let's talk about another parameter here. In our model, we have this distribution of starlight intensities, and we can ask the question, for the model, what fraction of the infrared luminosity is coming from either the dust grains heated by the delta function minimum starlight intensity, or what fraction is, say, coming from dust grains that are heated by, let's say, 100 times the local Milky Way starlight intensity or more. So the first of these would be the cirrus. This average starlight intensity would be dust in, say, the galactic cirrus of the Milky Way. And the answer is most of it. So the median fraction here is 88%. Most of the starlight luminosity, galaxy after galaxy, is coming from this low intensity component where the dust temperatures will be 17, 18 degrees for the big grains. And the fraction that's coming from regions where the starlight intensity is 100 or more times the local Milky Way average is only 8%. A small fraction of the luminosity is coming from these regions. And these would be the PDRs. So these are regions that are close to hot stars where the dust is illuminated by much more than the average intensity. And I was going to go through the logic of why that is, but in view of the time, let me just move on here to the PAH fraction. And that was just to show you that there's a lot of variation in PAH fraction. And here is the PAH fraction as a function of oxygen abundance. So below a critical oxygen abundance of about 8.1, the PAH fractions tend to always be low. And some of these may be essentially zero. Sort of we're down at the bottom range of our model making. But above this value, there's quite a wide distribution, but many cases where the PAH fraction is high, with a median here of 3.5% versus the 4.7% that we think, 4.6 or 4.7, that might apply to a galaxy like the Milky Way. And there are many examples of up at this high range here. Okay, so PAH fraction seems to be, for reasons we don't understand, connected with the metallicity. Now let me just show you some quick results here on spatially resolved observations. So what I've shown you so far were sums. We have images of the galaxies, but we summed over the whole image to have global values of the luminosity in each band. Here's what happens if we take the images of a galaxy, even a relatively large one like M51, but we degrade it to the resolution of the 160 micron camera on Spitzer. We have to do that because the dust modeling that we're doing here you need the long wavelength information to constrain the temperatures of the dust grains. So if you degrade the starlight distribution, you can't even see the spiral arms anymore. If you degrade the dust total infrared power, you can see the spiral arms a little bit. The dust mass per area, you can sort of see the spiral arms. They're not as conspicuous as they are in just the power. So the dust mass is not as concentrated as the spiral arms. And you can do the same thing for the PAH fraction. So for every pixel here, we independently derive the best fit PAH fraction. And now here's a color coding where red is from 4.2 to 4.9%. And you see much of this galaxy, M51, is red. It's the high PAH range. So they're not all pixels be exactly the same. But I think the coherence of this is quite striking, at least to me. They're not quite statistically independent because the PSF is a little bit more extended than these pixel squares. But if you go 2 pixels away, you're statistically independent of another pixel. Now, there's a little bit of evidence of fall off over here, but if you look over here, you see the signal to noise is not high. So I personally don't believe this fall off here. It comes out of the model fitting. If I take the uncertainties as given to me by the observers at face value, then these would be statistically significant. But then I look over here and I see, boy, there's not much flux there. What if they made some errors in the background subtraction? What if they, I'm not confident of this out here. But you notice also there's a little depression at the center. So the PAH fraction goes down a little bit at the center. There's a weak AGN at the center of M51. And if we do one other large example, M81, we see the same sort of thing. Where in M81, we can now see the spiral arms much more clearly because it's a bigger galaxy. Dust mass per area, so we think we track the spiral arms and the dust mass per pixel. And here's what the PAH fraction looks like. So notice there's quite a severe drop. We go all the way, much of the galaxy is up in this red to purple range of about 4.2, 4.5%. But the very center drops down to, somewhere in the 1.4 to 2.1. So the PAH fraction has dropped by more than a factor of 2 right here in the center, and I don't understand why. So this is a phenomenon that's been noticed, that AGN activity seems to be bad for PAHs. And maybe it's because of X-rays, maybe it's from something else. It's plausible that AGNs can do bad things to PAHs, but in fact, the quantitative understanding that it could do bad things to PAHs as far away as the effect seems to be is hard for me to understand. So there's a puzzle here. We see it in the observations, but we don't quite understand why. So one more thing. So I showed you photometry in galaxy after galaxy, and then I showed a model spectrum. But you're probably wondering, well, how well did the model spectrum actually reproduce the observations? So here is the spectroscopy of the central regions reproduced with the same PAH model. And you can see it reproduces it very well from the shortest wavelength. I should say the black line is the starlight plus dust model. The red symbols here, the vertical lines, are the is the IRS photometry from about here to here with the uncertainties. Some cases the uncertainties are big. In some cases the uncertainties are pretty small. So the model is reproducing the observations quite well over a broad range. So we're getting these PAH features right in galaxy after galaxy. So galaxies, by the time you average over a whole galaxy, the character of the PAHs is remarkably constant from one galaxy to another. Even though the PAH fraction varies, even though the temperature of the dust and the behavior of the continuum varies considerably, the PAH properties, at least averaged over galaxy scales, seems to be relatively standard. And here's just another sequence of these galaxies. So like this galaxy here, the error bars are there, but you can hardly see them. The model is falling right on top of the spectroscopy. And all we did was adjust the amount of PAHs and adjust the starlight heating to get the shape of the continuum right here. And the PAH the same size distribution for the PAHs is used in every one of these galaxies, just modulating the total amount up or down. Okay, so I think I better wrap this up here, and let me just show you, close actually on the previous slide here. So the future is going to be Herschel. So Herschel, we hope, is going to fly at the end of this year. And what's it going to do for us? Well, it's going to cover some of the same wavelengths. It's going to overlap in wavelength with Spitzer. It's going to go from 55 to 650 microns. But it's going to have an aperture which is 4 or 5 times larger than Spitzer, 4 times larger than Spitzer. It's not going to be entirely helium-cooled, so it won't have a sensitivity that's correspondingly higher than Spitzer. The instruments will be liquid helium temperatures, but it's going to have much better angular resolution. So those crude maps that I showed you of the dust mass on M51 will suddenly sharpen up when we have the Herschel observations to put into the model fitting. So we'll be able to say much more about the distribution of dust in galaxies. So let me just stop right there. Thank you very much. Okay, well, I don't think that's official, but you may be. I'm sure you're better informed than I am.
31st of October 2008,
Yeah.
but it's unofficially mid-January, and really it's going to be February. Have you looked at harder radiation field? You're just lowering the level of the radiation.
Yeah, we have looked at it. I don't have any.
AGNs especially, where there might be a harder radiation field.
Well, you think a harder radiation field, at least in the UV, would in fact raise the PAH emission, because the PAHs, we think, are very good at absorbing UV energy. And so it wouldn't explain this unless you hit the PAHs so hard that you destroy them. But it's hard to do that with optical photons unless you really blast them. So you need to get up to radiation intensities that are 10 to the 7th, 10 to the 8th times the local value here. And you have to be pretty close to an AGN to do that. So this optical starlight doesn't seem like a good way to go. X-rays might. So you might say might take a very small PAH and multiply ionize it by kicking an electron out of the K shell of the carbon and then having an Auger electron, and maybe the PAH was already ionized before that. Maybe you drive it over some ionization edge where it then explodes. But actually, then you think about it, it may not explode. It may just drive off 1 or 2 ions from its surface to get rid of the excess charge. So it's not clear that the destruction processes that we can think of are going to be able to act as far from the AGN as they seem to. So at least I have not understood it. Maybe.
Could it be blown out by radiation pressure?
Well, Norm can answer that, but I think it's, the PAHs don't suffer a lot of radiation pressures. You'd have to blow out all the dust, and what we're seeing here is a deficiency of the PAHs relative to the dust. In fact, the other dust would leave before the PAHs would. The normal grains are the ones that actually have big radiation pressure effects. So that seems to work the wrong way.
It might work because you could be exporting low pH. Like suppose you have gas near the AGN, it actually does destroy the pH, but then that gas gets blown out. But you do see alkaline.
Yeah, well,
Now mix with the ISM and reduce it. How long does it take to grow pH?
Well, we don't. So I should say we don't understand. At least I don't understand the origin of the pHs. And pHs are definitely fragile. They may not be so fragile to X-rays, but they're certainly fragile in a shock wave. So if you put them in million-degree gas, there's no question that they don't survive very long. And million-degree gas is produced by things that happen in star-forming galaxies and may happen in the nuclear regions of star-forming galaxies. So the issue may not be that there's all that much more destruction even, but that in the normal parts of star-forming galaxies, there are processes which somehow replenish the pH population, which aren't able to act with the same efficacy in the centers of AGNs. But that requires understanding the whole balance of pH abundances rather than just saying, oh, AGNs kill pHs. Because lots of things kill pHs, but galaxies know how to replace the ones that are killed. We don't know how they do it, but at least I don't, but it's happening.
You said only 8% of the dust luminosity PDRs can account for that. So you have interesting constraints on star formation rates?
Well, so this is a number which there are people in the PDR, business who try to explain all the complete emission spectra of galaxies by saying, oh, it's all PDRs, and oh, I see this galaxy is emitting this molecular hydrogen line. Well, I can explain it in my PDR model. I can get the same ratio of molecular hydrogen line to infrared emission in my PDR as is observed in that galaxy. But I claim you're only allowed to use maybe 10% of the galaxy luminosity in your PDR modeling. And it's not a surprising number because if you just think about where do PDRs come from, they come from massive stars. And if you ask yourself in a galaxy that's making stars steadily and has been doing so for at least 10 to the 9th or more years, basically all of the stars above 0.9 solar masses on the average, they're all steadily converting their hydrogen into heavier elements and producing energy. And so the fraction of the mass which you're putting into the mass distribution is the fraction of the luminosity you're getting out. And for the IMFs that we think are applicable to the Milky Way and other galaxies, 90% of the mass is below 20, between 20, well, the ratio of the 0.9 to 20 solar mass to more than 20 is about 8 or 10%, maybe 15%. And then you consider, okay, it could actually be higher because massive stars do sometimes get away from the regions. There are runaway O stars which don't have PDRs around them. And so this number of 8 or 10% is a perfectly reasonable number. In fact, it'd be shocking if it were much higher.